All right, so we are meeting after a week. So let's just quickly talk about where we left off the last Friday. We were talking about the signed magnitude representation of signed numbers. And we looked at how to add numbers using signed magnitude representation. We also looked at how to subtract using signed magnitude representation. One of the things that was problematic with signed magnitude arithmetic is that we needed a unit to do addition, we needed another unit to do subtraction, and we also needed a unit to compare the magnitudes of the numbers because that would determine the sign of the result. There was no way to do signed magnitude arithmetic without these three units, and hence signed magnitude arithmetic leads to a very complicated implementation, which requires all these three units. Of course, we don't want so many units just to do addition and subtraction. These are supposed to be very, very fast computations as far as your computer is concerned. So we need another way to represent both positive and negative numbers so that we can do this arithmetic with lesser number of units, meaning lesser hardware and faster computations, right? Lesser the hardware, faster the computation. So what we are doing is we are not changing the units itself, we are actually changing the way we represent numbers. We also looked at overflow conditions, meaning if you are adding two numbers or you are subtracting two numbers, because we have a limitation on the number of bits we use to represent signed numbers, our result of addition or subtraction could fall outside the range of the numbers that we represent using n bits. So for example, if you had 4 bits to represent signed magnitude numbers, these 4 bits should be used for the numbers as well as for the result. Meaning with signed magnitude with 4 bits, you get a range of -7 to +7. So if you took a number, for example, 5 plus 3, when you add it, the answer falls outside the range, meaning the number of bits, 4, not enough to represent 8 plus 8. That's an overflow condition where your answer, result, falls outside the range. And you can detect that by monitoring the carry in into the sign position. So if the carry in, highlighted in pink here, is a 1, that indicates overflow. This applies for signed magnitude arithmetic. A different scheme is going to be developed for two's complement representation. Now, if the carry in bit for the sign position is 0, that means no overflow has occurred. And we verify that by using these examples. So that's where we left off. Now, what we are going to do is essentially this slide summarizes the things that we just talked about. Addition, we need something to add, we need something to so let's see, we need an adder unit, we need a subtractor unit, and we also need a comparator. To do subtraction, we need subtraction or addition. It depends on whether the sign of the operands is the same or different. And we looked at examples for doing that. And also a comparator to determine the sign of the result. All of that ends up in needing these three units, adder, subtractor, and comparator. We can do better with 2's complement representation. So let's take a look at that. Now, 2's complement representation deals with subtraction in a different way. So the way 2's complement representation deals with subtraction. So for example, if you are going to do a plus b, that's fine. The addition is what we used. An adder unit is what we use to add a and b. It's going to be similar to what we have been seeing so far in terms of addition of binary numbers. But in terms of subtraction, we are actually going to represent subtraction as pseudo addition, meaning I will convert a minus b to a plus the negative 2's complement representation of b. That way, I just need an adder unit. I need an adder unit to do that. I need an adder unit to do that. So what I'm doing is, if I'm trying to do subtraction a minus b, I'm converting b into its negative 2's complement representation and then carrying out the addition. That way, I can just use adder. I don't need a subtractor, and I actually don't need a comparator as well. We'll take a look at more examples about how this happens. Now for 2's complement representation, again, because it's a signed representation, we need to worry about how many bits are we going to have to represent those numbers. So here we are taking a look at 4-bit example, and we are representing +3 and -3 using 4 bits in 2's complement representation. This is the most commonly used form of representing signed numbers to perform arithmetic. +3, exactly the same as signed. First bit representing the sign, we had 4 bits, so the remaining 3 bits are representing the magnitude. 0, 0, 1, 1, positive 3. So for positive numbers, 2's complement representation remains the same, no problem. But for negative numbers, here is where you will see the change. The first bit here is 1, that indicates negative number. But then there are 1, 0, 1. It's a different sequence of bits, and the claim is that it represents 3. Now let's see where it comes from. How is that 1, 1, 0, 1 representing -3? Well, for that we need to look at the definition of 2's complement representation. The definition of 2's complement representation is, if you want to represent a number cap n in its -2's complement form, then you need to subtract it from 2 raised to small n being the number of bits. So this guy is small n is the number of bits. So for 4-bit example, small n would be 4, right? So let's see if we can redo this same case here for -3. Over here, n is 3. And I need to find the -2's complement representation of 3. So that would be -3 represented in 2's complement form will be what? 2 raised to small n minus cap n. So 2 raised to small n is 4, 4-bit example, minus 3, which is cap n. So that would be what? 16 minus 3, 13. How do you represent 13 in decimal using 4 bits? Well, you represent that as 1101. Exactly the same as what we did over here. First bit comes out to be 1, negative. It satisfies the notation that we have been following, and the remaining 3 bits are not directly magnitude, they are related to the magnitude, right? So that's the key difference between 2's complement representation and signed magnitude representation. The bits that we used for the magnitude are related to the magnitude, but that is not directly related. That's not directly the representation for the magnitude. We will take a look at a few more examples about this. But that's your definition of 2's complement. Do we always have to use this? Actually, no. We are going to simplify this definition. We are going to make it a lot more easier to use this definition. Some of the consequences of using 2's complement representation are only one representation for 0. 0 is represented using 4 bits as 0, 0, 0, 0. That's it. There's no 2 representations like we had in the case of signed magnitude. Remember, for signed magnitude, 0, 0, 0, 0 was representing 0, and also 1, 0, 0, 0 was also representing 0, in that it was -0. So we were losing one of the 16 combinations for the same number. We don't have that problem anymore. In fact, later on, we will see in 2's complement representation, what does 1, 0, 0, 0 represent? We will take a look at that in just a bit. So by doing that, we get one more negative number than positive number. So in the 16 cases, you will have one more negative number than the positive number. So the range of 4 bits actually goes from -8 to +7. So you get one more. Again, we will formulate generic range of 2's complement numbers in just a bit. Same as always, the most significant bit indicates the sign. and positive numbers are going to be the same as in sign magnitude. So at least for the positive numbers, we don't have to worry about converting them into their negative 2's complement representation. They are going to be the same as sign magnitude. How do we get 1101? We just talked about that using the definition of 2's complement, 2 raised to small n minus cap n. But we are also going to work on simplifying that process, simplifying the definition. So let's talk about this. Actually, we did this, right? Let's take another one. Let's take something else. Let's take -9. What is the problem here? Can I do this? No. Out of range. Perfect. So I can do this. I'm going to erase this number again. And I'm going to choose something from the range. Say like -7, right? So if I want to represent -7 in its 2's complement form, notice over here, I have explicitly talked about the number of bits. I've reserved it for 4 bits. So that helps me. So -7 in its 2's complement representation is going to be 2 raised to 4 minus 7. 16 minus 7. What is that going to be? 9. Oh, hold up. I got 3 from there, 6 from there, 9. Yes. So 9 represented in binary, what is that? Using 4 bits. 1, 0, 0, 1. First bit came out to be 1 for negative. That's good. And then 1, 0, 0, 1, that's what represents -7 in signed 2's complement form using 4 bits. If I used 5 bits, what would change? If I were to use 5 bits, what would change? Instead of 16, you would have 32. Okay. But if you did everything the same way, I'm going to claim that it will result in 1, 1, 0, 0, 1. Just an addition of 1 at the very end. So you're adding more and more 1's to the left. As you add more and more 1's to the left, the negative number will not change. The same way as you add zeros to the left of a positive number, its value doesn't change. Right? So I can take a positive number plus 5 and add 0.5 and 0.05. Its value doesn't change. In the same manner, if you have -5, you start off with a 1 at the front. If you add more and more 1's to the negative number to the left, you are not changing its value. That is called sign extension, right? Extending the sign. More about this later. Let's come to negative numbers in 2's complement form. We talked about the fact that we need to fix n, right? Number of bits have to be fixed, and that's the definition. We also looked at that just a bit ago. -n represented as 2 raised to small n, where small n is the number of bits we are using minus the number itself. Now you see this example we just did, right? 2's complement representation of -7. We just did that, 1, 0, 0, 1. We got that same answer. That represents -7. How about +7? For +7, we would do 2 raised to 4 subtracted from -7. That would give us 0, 1, 1, 1. That is how you represent 7. And it is consistent with sign magnitude representation. So that definition applies the same for negative numbers and positive numbers. But for positive numbers, I don't need to worry because it's going to be the same as sign magnitude representation. How about 56? I want to represent 56 in its 2's complement form. How do I do that? First, talk about the number of bits, right? 7. I have associated 7 bits with that. And the good news is with 7 bits, I can represent negative 56. So I have verified that. Let us look at a simple way of doing this. And once I talk about the simple way of doing this, I will talk about how the definition. So Ajit says, Ajit is absolutely right. You would do 2 raised to 7 minus 56 and represent it in binary form. That's from the definition of 2's complement. But what I'm going to do here in this example is actually a shortcut, right? And later on, I will relate the definition and the shortcut. I will connect the two later on. But I want to show you the shortcut first. The first step is going to be for me to place 7 positions. Let me do
the shortcut.
Yes, a shortcut. 1, 2, 3, 4, 5, 6, 7. Yes, I've got 7 places here. And that is going to be in binary 2's complement representation. So is there a bit I can fix here?
The first one is negative.
First one is negative. Beautiful. This is 1 negative. So, okay, let me use blue. I'm done. I'm done with the sign, right? I need to now worry about the magnitude. This is going to be the steps. So let's say first step is going to be start with positive 56. Start with positive 56 and try to represent that in binary using 7 bits. And if you do this, you will get this 0, 1, 1, 1, 0, 0, 0. And you can verify this later. If you convert 56 to binary using 7 bits, you should get that. You get 1 for 32 place, 1 for 16 place, 1 for 8 place, and everything else should be 0, including the sign. Now, you have represented 56. The second step is going to be, this is the shortcut, right? So flip, meaning complement each bit. So if I complement each bit, what do I get for plus 56? I get, let's see, 0 complement, 1 complement, 1 complement, 1 complement, 0 complement, 0 complement, 0 complement, which will be 1, 0, 0, 0, 1, 1, 1 in binary. The last step is to add 1. Add 1 to it. Add 1. So what do you get? 1, 0, 0, 0, 1, 1, 1 plus 1. Carry out the sum and carries. You've got 1 plus 1, 0, 1. 1 plus 1, 0, 1. 1 plus 1, 0, 1. 1, 0, 0, 1. That was my sign. That is my number. That's your answer. 0, 0, 1, 3 zeros. So the shortcut is, why did you add 1? Oh, so why did I do this? I will explain in just a minute, because I need to connect the definition of 2's complement to this shortcut. I need to do that. So hang on to that question. But that's your shortcut, right? So to reverse translate, we flip again and convert to base 10. You flip again and add 1 to convert to base 10. We will take a look at that example as well. The name of this method is to convert numbers to their 2's complement representation. That's the name, right? There's no special name for this. Flip all the bits, add 1 to it. Now there was a question about reverse, right? Going back. Let's take a look at that. Now to go back, I need to talk about number of bits again. So number of bits, I'm going to just assume 5. Number of bits, 5. Okay, so if I have a 5, tell me, is it a positive number or a negative number? That's the first question. Negative. All right, you guys got that right. It's going to be a negative number because this guy is a 1. Now, I need to find the value of that negative number. Now, in order to find the value of that negative number, I carry out the same process again. Complement each bit and add 1. All right, so if you complement each bit, what do you get? 1 complement, 0 complement, 1 complement, 1 complement, 0 complement becomes 0, 1, 0, 0, 1. Next step, add 1 to it. What does that become? This is in binary, this is in binary, everything is in binary. 0, 1, 0, 1, 0. What is that? 10. Perfect. So your answer is negative 10 in decimal. You got negative from here, you got 10 from here, and that's how you get your answer. So flip all the bits and add 1, right? That's as easy as it can be. Now, you can also check this, right? You can also check this by converting negative 10 to its 2's complement form using 5 bits, and you should get that. You should get your original sequence of 5 bits, and you can do that as well, right? So that's a good way of checking whether you are on the right track or not. You can do that. Let's do it. Here, I've got negative 10 in its decimal form. I want to find out what is it in 2's complement form using 5 bits. So what do? I start with, first step was what? Start with 10. 10 represented using 5 bits will be what? 0, 1, 0, 1, 0. In binary. Second step is what? Add 1 to it. Oh, sorry, not add 1. That is the third step. Complement each bit. When you complement each bit, what do you get? 1, 0, 1, 0, 1. Third step. Add 1. What do you get? 1, 0, 1, 1, 0. Does it check out? 1, 0, 1, 1, 1, 0, 1, 1, 0. 1, 0, 1, 1, 0. Right? So if you are in doubt, you can always check that the way we just did. Right? So this is our check. Let's move on. Talk about the range of 2's complement form. And at the bottom of this slide, we also have the range of signed magnitude form using n bits. Where do you add the 1? So where do you add the 1? All the way to the right, right? So when you're doing 1, 0, 1, 0, 1 plus 1, all the way to the right. It's always to the right, right? 56 plus 1, you always add to the right, right? How did we get the bit ranges again? Well, we didn't get the bit ranges just yet. That is how we get the bit ranges. So the range of 2's complement using n bits will be negative 2 raised to n minus 1 to positive 2 raised to n minus 1 minus 1. We lose 1 bit for the sign. And we gain 1 position on the negative side because we have saved negative 0. That's the difference between sign magnitude range and 2's complement range. So for example, if you had 5 bits, what would be the range here? It would be negative 16 to positive 15. But using 5 bits for sign magnitude, you would have negative 15 to positive 15, right? Yes, so Adrian asks a question. Will you always tell us how many bits our answer should be for? Yes, I will have to explicitly tell you how many bits you will need to use. If I don't tell you how many bits to use, then you would have to assume the number of bits that you are using. But when you assume the number of bits, you just have to make sure that your number is within that range, within the range that can be represented using those number of bits. Let's see, how is the negative factored in? Well, you see this. If I have 4 bits, well, let's talk about 5 bits. If I have 5 bits, I have 32 combinations, right? If I have 32 combinations, I'm trying to represent positive numbers and negative numbers using for 32 bits. Half of them roughly are going to be negative, half of them are going to be roughly positive. But because of 2's complement representation, I gain the negative 0 with an addition of one more negative number, minus 16 in this case. So that's how you are getting the half of them positive, half of them negative, roughly. But those are generic formula, those are generic range calculations for 2's complement, and in the bottom you have sign magnitude. Now let's try to connect the two. Is the only reason to use 2's complement over sign magnitude the extra negative? No, that's not the only reason. Actually, the main reason is to simplify our arithmetic. The main reason is to simplify the arithmetic. I no longer need comparator. I no longer need subtractor. I just need 2 things. One, the adder unit. The other, the ability to make numbers into their 2's complement form. Quiz 3 problem 1 asks for the range that can be represented using 5-bit sign magnitude. You're saying negative 16. No, I'm not. I see. Look at this. That was for 2's complement. This is for sign magnitude. So the last class was about sign magnitude. That's why I asked the question on the quiz about sign magnitude. All right, let's try to get to the most important relation, right? There is a shortcut, there is a definition. How are they two connected? You don't believe the shortcut. Let me prove it to you. So what was the original formula? The original definition of 2's complement was you can represent a number in its negative 2's complement form by doing 2 raised to small n minus cap n. Now I can rewrite 2 raised to small n minus cap n as 2 raised to small n minus 1 minus n plus 1. So I just added and subtracted a 1 to this, right? So they cancel out and I get back what I have on the left side. Now we are going to try to understand what that is. 2 raised to small n minus 1. You guys remember we did this a few, we did this last time. Where is the table? Where is my table? Right here. You guys remember this? 2 raised to small n minus 1 will always be a string of ones. How many ones? Small n. We did this exercise the last class, right? We started with 1, 3, 7, 15, and so on, and we saw that all those numbers in decimal will always having ones, string of ones, 1 1, 2 ones, 3 ones, 4 ones, and so on up to n ones. So 2 raised to small n minus 1 will always be a string of ones. We did this in the last class. We are going to need, the reason we did that was this. 2 raised to small n minus 1 will always be a string of n ones. Now what are we doing? To get this formula, we are getting to all ones minus n, right? So let's focus on this. Let's focus on 2 raised to small n minus 1 minus cap n. And the claim over here is 2 raised to small n minus n will always be bit by bit complement. Let me prove that to you right here. What I'm going to consider is a number n which is made up of 4 bits. My least significant bit is n sub 0. My most significant bit is n sub 3, right? So I'm just assuming that my number cap n is being represented using 4 bits. And what do I need to do? I need to do string of ones. That was what? That was 2 raised to small n minus 1 minus n, right? So that's what I had to subtract. And the claim is that it will be a complement, bit by bit complement. Let's prove it. String of ones. How many ones do I need to consider over here? Well, I just have 4 bits for n. I'm assuming 4 bits. So I'm going to simply write 4 ones. 1, 1, 1, 1. And I'm going to subtract the number n3, n2, n1, n0 from it. What happens? Well, you will get this result, right? For the least significant position, you get 1 minus n0. Next to that, you get 1 minus n1. Next to that, you get 1 minus n2. Next to that, you get 1 minus n3. Okay, so 1 minus n0, 1 minus n1. Okay, so let me do this. What can be the two values for n0, n1, n2, n3? 0 or 1. Perfect. So let me do this. I will make that into a variable, 1 minus x, right? So instead of saying 1 minus n0, n1, n2, n3, I will just say 1 minus x. And you guys just said x belongs to 0, 1. X is a binary variable. It can take a value of 0 or it can take a value of 1. When x equals 0, what do you have? 1 minus x will become 1 minus 0 will become 1. Zero got complemented. Let's do the other case. When x is 1, 1 minus x will be 1 minus 1 will be 0. 1 got complemented. So 1 minus x is x complement. You guys see that? So what can I say about this? 1 minus n0, n0 complement, n1 complement, n2 complement, n3 complement, bit by bit complement. That was the first step, right? That was the first step in 2's complement representation. Do a bit by bit complement. That's how it comes from. That's how we are relating the definition to the shortcut. Let's go back. So we have proved this. We have proved this statement. 2 raised to small n minus 1, that is a string of ones, minus n will be a bit by bit complement of n. What is left? The plus 1 is left. That's your third step. Add 1 to the number. That's because of this guy. So I hope now you are able to make that connection between the shortcut and the definition. And there are two examples over here. One is to represent -7 and the other is to represent +7. And they are both being represented using a 4-bit number. 4-bit number. So what do you have? For -7, you will start with 0, 1, 1, 1. That is +7. You will complement all the bits and add 1 to it. You will get 1, 0, 0, 1. That's a representation of -7. Similarly, for +7, what do you have? 1, 0, 0, 1. That's the representation of -7. Complement each bit, add 1 to it, you get representation of +7. Actually, for positive numbers, I would just recommend you to not get worried about the definition. Just use sign magnitude representation. For positive numbers, it works out quite easily. For negative numbers, you need to do that negative, flip all the bits and add 1. All right, we'll see more examples. Now, that's an interesting question. What is the decimal value of 1000? So I'm using 4 bits. So let me just say 4 bits. What do you think the value is? In sign magnitude representation, it would have been -0, right? In 2's complement form, it'll be something else. 4 bits, 4 bits. So first of all, let's decide whether it's positive or negative. Positive or negative? Positive or negative? Negative. All right. Negative is right. The most significant bit is 1, so negative number. Beautiful. What is the value? Take all the bits, flip them, add 1 to it. 0, 1, 1, 1 plus 1. 1, 0, 0, 0. 8. So you got what? 1, 0, 0, 0 in binary, 2's complement form went to -8. Now you see, you are right, -8. Now you see where we gained that one extra negative number. We saved -0 and we got -8 for it, right? That's how we gained that one extra number for 2's complement form. So whenever you see 1 followed by a bunch of zeros, it will be -8 or -16 or -32 and so on. A few things that we need to all keep in mind when you are dealing with 2's complement numbers, and must be fixed. The number of bits must be fixed, explicitly talked about. To convert a positive number to negative number, you complement bit by bit, then add 1 to it. To convert a negative number to a positive number, complement bit by bit, then add 1 to it. Same procedure, but for positive numbers, you don't even have to do this. You can just use sign magnitude representation for 2's complement, because the definition and the sign magnitude representation are consistent for positive numbers. Now let's talk about what would happen to these numbers as you are adding or subtracting positive numbers. Now, if you look at 4 bits, right? So we are assuming that we have 4 bits and we can represent -8 to +7 with 2's complement form. All those 16 numbers have been put on a circle. -8 all the way to +7. And there is a dotted line over here that indicates overflow outside the range with 4 numbers, right? You can't be there. If you are there, that means overflow has occurred. As you are adding positive numbers, so for example, 2 plus 5, 5, you are going clockwise. As you're adding positive numbers, you move clockwise. As you're subtracting positive numbers, you move counterclockwise. But in both those cases, you could end up in this region where you could have an overflow. So with 4 bits, if your result is less than -8 or more than +7, that means you have an incorrect result, invalid result, out of range. Let us try to look at 2's complement calculations. Now, as we are going through these calculations, you will see that the arithmetic gets simplified a lot. 5 plus 3 using 4 bits. So all of this is 4 bits. Let me just write this. 4 bits. All of them are 4 bits. So things should be between -8 to +7. Hold up. What? Oh, yes. So 5 plus 3. What did you expect the answer to be? 8. +8. But what did you get? -8. That means overflow has occurred. So you wanted +8, but you got 1000, which actually means it is -8 in 2's complement form. So remember, the numbers are represented in 2's complement form. The answers are also represented in 2's complement form. All are in 2's complement representation. 5, 3, and the answer. In this case, an incorrect answer, invalid answer. Another way of detecting overflow in 2's complement arithmetic is positive plus positive cannot be negative. Invalid. Overflow has occurred. Negative plus negative cannot be positive. Overflow has occurred. Tyler says if you bring down the 0 in front, well, you cannot. So the goal is to not do this with 5 bits. Yes, you are right. We have a fix. 4 bits. Yes, the goal is not to exceed that. If you have unlimited number of bits to represent numbers, then you will never have overflow. So idea is this. If you have 4 bits and you are adding numbers, then you may have overflow if the numbers get added to be outside the range. So because you had 8 here, you actually got an invalid result, 1000. The reason for that was overflow. You expected something, you got something else. That's invalid result. The way to check that, there are many ways to check that. If you are looking at the number itself and the number, so not this number. If you're observing the number itself, the expected number, and if that falls outside the range, you know overflow has occurred. Another way of indicating overflow or detecting overflow is positive plus positive cannot be negative. Negative plus negative cannot be positive. If it is, overflow has occurred. So in both these cases, so here, what did you expect? -9. What did you get? +7. Invalid, incorrect, overflow. Here is the good news. When you do this right, 5, 2, 7, -3, -5, -8. You don't have a problem. You got the right answer. 0, 1, 1, 1 is 7. 1, 0, 0, 0 is -8. In its 2's complement representation, everything worked out. Positive plus positive is positive. Negative plus negative is negative. All good. This is when you are doing, the addition, right? over here, all the numbers have the same sign. If one of the numbers has a different sign, all that changes is the number that has a different sign, you will need to convert it into its 2's complement representation. Now, there's another question on the chat box, which is the third way. The third way to represent, hold up. That is the third way to detect overflow. If the two most significant carries, one into the sign position, the other out of the sign position, if they are different, overflow has occurred. Different, overflow has occurred. Same, no overflow. Same, no overflow. So essentially, you have many ways to detect overflow here, right? First way, if you're looking at the expected result and if that falls outside the range, overflow has occurred. Second way, positive plus positive cannot be negative. Negative plus negative cannot be positive. If it is, overflow has occurred. The third way is to observe the carries that are into the sign position and out of the sign position. If they are different, overflow has occurred. If they are the same, overflow has not occurred. Right, so there are many ways to detect overflow here. Let's keep moving. So what did we save? No need of comparator. I don't need it. I can just do the addition or pseudo addition and get my result. I don't need to compare. Let's actually do this. Let's actually do an example. Let's do an example. Well, we'll do examples later with fractions as well. So we'll take a look at more advanced examples at once. So for 2's complement, when you're doing addition, it doesn't depend on the sign of the operand. No need to compare the magnitudes to determine the result. You just add them and look at the most significant bit position. If it is positive, answer is positive. If it is 1, the answer is negative. Subtraction. Subtraction is treated as addition, pseudo addition, I call it, right? Add the negative to the subtrahend to the minuend. Can you explain the 2's complement clock again? Well, it's not really a clock. I would just say this, right? So if you put all the numbers that are in the 2's complement representation using 4 bits on a circle, think of this guy as something that can move clockwise or anti-clockwise when you are adding numbers or subtracting positive numbers. So if you are adding numbers, for example, 5 and 2 plus 2 plus 5, you move clockwise. And you may end up in overflow region if you cross over plus 7 for the answer. If you are doing subtraction of positive numbers, then you are moving counterclockwise. 5 minus 2, you're moving back. Right? So, sorry, subtraction of positive numbers. You're moving counterclockwise in that case. -2, -5, -7. Can you go over 1000 is -8? Hold up, guys. So, I also need to be a little bit careful about my time. Right, so let's see, where did we do negative? Right here. So 1000, the first bit is 1, so a negative number. I need to find the value. If I want to find the value, I complement all the bits and add 1 to it. When I complement all the bits, I have 1000 complemented to 0111 and I add 1 to it. So that was 7, that was 1, so I got 8. -8. All right, so let's move on here. Okay, so here. Now, when you're doing 2's complement arithmetic, you will need only 2 things. One, adder unit. The other, a circuit that can compute 2's complement of numbers. So a negation circuit unit. We also need an ability to add 1. And actually adding 1 is not a big problem because I can assume the initial carry in of numbers to be a 1, right? So whenever you are adding numbers, say for example 1001, 1101, when you are adding two numbers, we usually assume a carry in, initial carry in of a 0, right? But if it is a negative number and I'm trying to represent it in its 2's complement representation, I can just make that initial carry a 1. That's how I can add a 1 after I do a complement bit by bit, right? So I really need two things. One is adder unit, the other is something that can do a bit by bit complement or the negation circuit. That's it. I can do addition, I can do subtraction. No need of comparator, no need of a separate subtractor unit. How about fractions? You guys have seen this before, right? How do you represent 5.23 in decimal to in its positional significance? Each digit 5, 2, and 3 are being multiplied by their corresponding index. 10 raised to 0, 10 raised to negative 1, 10 raised to negative 2. And for binary numbers, you have 1, 0, 1, 1, but there's a binary point in the middle. So for things on the left, you have increasing powers of 2. For things on the right, you have decreasing powers of 2. Now, 2's complement representation is going to work even for fractions. And I will go through an example with this. Here. This is a very interesting example, and I hope that you guys are on your A game right now. We are going to try to represent negative 2.75 in decimal in its 2's complement signed binary fixed point notation. And I have explicitly said I need 3 bits for sign an integer, and I have 3 bits for the fraction part. So how do I do this? Well, a lot of these steps are going to be exactly the same as the steps that we had for converting negative numbers to their 2's complement representation. What was the first step? Step 1 was represent positive 2.75 in binary. Okay, so how do I do that? I need 2 and I need 75. You got it. We just did it over here, right? 2.75. All right. So 2.75 in decimal is going to equal, I have 3 bits for sign and integer. That is my sign and integer. Binary point. And for 75, I need half and a quarter. Half and a quarter. That's my first step. Representing the number in its positive form. You are asking the absolute right question. Which bit to add plus 1? That's the right question. The answer is all the way to the right. So let's do this. Second step is what? Flip all the bits. Okay, so this will become what? 1, 0, 1, 0, 0, 1. I've just flipped all the bits. The third step is to add 1. When you add 1, you add it all the way to the right. So what you do is this: 1, 0, 1, 0, 0, 1, add 1. You can always multiply by 2 raised to 3 and then divide by 2 raised to 3 to move that binary point. So you are going to add all the way to the right. You get what? This is going to be 0, 1, 0, 1, 0, 1. Yes, you got it. So the answer here would be and again, you can check this. The way you check this is flip all the bits, add 1 to it. You already know it's a negative number because the most significant bit is a 1. Let's do that. This guy is a 1. So I know it's a negative number. I need to find the value. What is going to be the value? Well, take 0, 0, 1, 0, 1, 0, flip all the bits, add 1 to it. What do I have? 1, 1, 0, 1, hold on, wait a second. So to find the value, why did I choose this? I have to use this. Right, flip all the bits, add 1, okay, so 0, 1, 0 dot, binary point 1, 0, 1 plus 1, 0, 1, 0, 1, 1, 0, 2, 7, 5, negative 2.75. All right. When we are dealing with fractions, there is a very good possibility that you might not be able to represent the number exactly with the given amount of bits, given number of bits. Consider this example. When you're trying to convert 0.34 to binary, what do? Well, we can successively multiply by 2 and record the integers, right? That's our process. We looked at this in the previous 2 classes. So as you are multiplying 0.34 by 2 continuously and you are recording the integer part of the result, what did you have? You got a 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0. So it keeps on going, right? This is not going to end. What does that mean? That means that you might have an error while representing some numbers like this, right? So this keeps on going. So for example, if you had a limitation on the number of bits, for example, over here, how many bits do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bits. With 10 bits on the fraction, you were only able to reach 0.33984. You were not able to reach 0.34. How can I increase the accuracy? Well, use more bits. Instead of using 10 bits, use 11, 12, 13, keep on going, right? So that depends on your application. How precise do you want the numbers to be? The more precise you want them to be, the more number of bits you would have to assign to them. But the goal of this slide is to indicate that it is possible for certain numbers to have that representation error. For example, let's make this a little bit more dramatic, right? What if you had only 2 bits? What if you had only 2 bits to represent this? You could only do how much? .25. Yes, absolutely, right? With only 2 bits, you see the error is huge. With 10 bits, well, the error is not huge, right? So the point of this slide is the more number of bits you have, the more precise your number representation is going to be, and the lesser error you will have. Is this a reason why it was hard to? Yes. For that, we would need a lot of bits. So this goes into IEEE 754 standard of representing 32-bit numbers or 64-bit numbers. So IEEE 754 single precision format, which deals with 32-bit numbers, has, let's see, 32-bit numbers use 1 bit for sign. They use 8-bit for exponent and 23 bits for mantissa. And they can be used to represent very, very, very small numbers to very, very, very large numbers. more details about this, how to convert and what are these, yes, so mantissa, exponent, all of those details are in the other course. Details to this ECSE 2660. For 64-bit format, I just want to show you that with more number of bits, you can get a very, very precise number. So for example, with 32, you will have a range. With 64, for example, the range of numbers you can represent goes from plus or minus 10 raised to negative 323 to 10 raised to positive 308.3, right? So a very, very big range. Yes, next semester. In this case, 64 bits, 1 bit is for sign, we only need 1, 52 bits for significant, and 11 bits for exponent. This is just to demonstrate that precision can be increased by increasing the number of bits, and you can actually use that for a very, very big range, representing numbers that are extremely small to extremely large. Those are floating point numbers. We have been dealing with fixed point numbers here. All right, let's move on. Binary codes. Now for decimal numbers, we know that humans are very comfortable with decimal numbers, right? You guys have been doing this since elementary school. Now you can represent decimal numbers, the symbols in decimal numbers. What are they? 0 through 9, right? 0 through 9 using binary coded decimal, or you could do this using 2421 code, which is a weighted decimal code, or you could represent decimal numbers or symbols using 1 out of 10 decimal code. We will take a look at an example of that. We will just fill out this table. So all the way to the left, you have the 10 symbols that we use in decimal representation, 0 through 9. So binary coded decimal is the 8421 weighted code. So each position is weighted 8, 4, 2, and 1. So with 8421, 0 would be represented as 0, 0, 0, 0. 0 times 1 plus 0 times 2 plus 0 times 4 plus 0 times 8 equals 0. 1 would be represented as 0, 0, 0, 1. 0, 1, 0. 8421 is the same as binary, but only 4 bits. Yes. So 3 would be what? 0, 0, 1, 1. 4, 5, 6, 7, 8, and 9. Done. So that's your 8421 code or binary coded decimal. Now, here is an interesting code, 2421. This code is actually called self-complementing code. How can I get 2421? Well, for 0, it is quite simple, right? For 0, you would say 0, 0, 0, 0, right? 0 times 1 plus 0 times 2 plus 0 times 4 plus 0 times 2, 0. How about 1? That works. How about 2? That works. 3, 4. So far, so good. Why did I call it self-complemented code? Here, yes. So hold on to that question, just a second. Why did I call this a self-complementing code? The reason why I called it a self-complementing code is because I came up with half the numbers. The other half is going to be exactly the complement. What is the complement bit by bit of 0, 0, 0, 0? 1, 1, 1, 1. Perfect. 1 times 1 plus 2 times 1 plus 4 times 1 plus 2 times 1. What did I get? 9. You guys see that? Those are related. Take all the bits, flip it, and you get the other end. All right, so tell me the code for 8. What would I need to do for 8? What should I fill here? You got it. 1, 1, 1, 0. Complement, 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 complement. Next, for 7, 1, 1, 0, 1. For 6, 1, 1, 0, 0. For 4, 1, 0, 1, 1. Maybe blue? Sure. And then I can do pink. You guys see that? So that's your self-complementing code with weights 2, 4, 2, 1. Next, 1 out of 10 code. Actually, that's the simplest. 1 out of the 10 bits will be a 1. For 0, it will be the first bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Next, for 1, next position. Next position. Next position. Oh. You guys see that? And the last one will be all zeros. Last one will be 1. 1, 0, 0, 0 do not exist in 2, 4, 2, 1. Yes, you are right. It doesn't. So those are 3 codes that you can use to represent decimal numbers. Let's do some examples. How do I represent 12 in decimal using 2421 code? I need a 1 and I need a 2. Okay, what is the symbol? What is the 2421 code for 1? 0, 0, 0, 1. Yes. How about 2? 0, 0, 1, 0. Done. You got it. Yes. Let's do another one. 905. 9, 0, 5 is the complement of 4. I think it is 1, 0, 1, 1. All right, so I think that's we covered pretty good. Now let me do this. I want to spend some time talking about the half adder. We got 10 minutes left. In this 10 minutes, I want to talk about the half adder. Half adder is used for what? Adding 2 numbers at a time, right? So if you have 2 bits A and B and you're trying to add them together, you will get 2 outputs, sum and carry out. We actually did the truth table for the half adder in the previous class. We had 2 bits for A and B. We had 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. And you had 2 outputs, sum and carry out. The sum was either a 0 or a 1 and a carry out was either a 0 or a 1. And in fact, the carry out was a 1 only when you added 1 and 1. So 1 plus 1 is 2. 2 in binary can be represented as 1, 0. 0 goes as sum, 1 goes as carry, right? Now my goal in the next few minutes is going to be to discuss about all these things. Block diagram, truth table, logic expression, and a logic diagram for the half adder. Block diagram, very simple. 2 things on the left representing input, 2 things on the right representing the output. A and B are your 2 bits as input. S and C out are your 2 bits as output. Half adder HA, that's your block diagram. Now my goal is to find out what is inside this guy, right? So I'm going to try to represent the inside of the half adder using a logic diagram. Let's start talking about a logic expression for sum, that is S. Sum is a binary variable. It could be a 0, it could be a 1. So it's a binary variable. It's an output binary variable. A and B are input binary variables. They could have a value of 0 or they could have a value of 1. Now, a logic expression is a relationship between input and output variables. You guys have written a logic expression for Studio 0. That was C equals A and B. That was a logic expression relating the output to the inputs. Many of you have also written logic expressions for Studio 1, for the 2-bit comparator. Those were relationships between the output. Each output was represented using some or all the inputs. So a logic expression is nothing but a relationship between inputs and outputs. In this case, input and output variables. So let us try to establish the logic expression for S, the sum. So to do this, I will ask a simple question. When is the sum 1? Well, the sum is 1 here and here. 2 places. Those 2 places, I can write it like this. Sum is 1 when A is 0 and B is 1. Now A is 0 can also be represented as A complement is 1, right? So you see what is going on. A is 0, that means A complement is 1. And for S to be 0 for the first case, A complement has to be 1 and B has to be 1. Similarly, for the second case, S is 1 when A is 1 and B is 0, or B complement is 1. So you see what we did here. We said A complement is 1 and B is 1. Or the other way the sum can be 1 is A is 1 and B complement is 1. Now, both these conditions only go for the places where sum is 1. So what we get as a logic expression is actually called a sum of products expression. We will talk more about these expressions later on in detail, because this is a sum of products, but there will also be a products of sum, where we will be focusing on the zeros in the column of S, or output. So these 2 statements combined, statement 1 and statement 2, I can write sum as A complement and B. You see, and I'm using a dot, the product sign. A complement and B, A complement and B. Or, this is my pink, or, and then this is my blue for and. Let me erase this guy, this guy, this guy, this guy. Actually, let's do a color code for this. Let's do maybe a green. A complement right here. Next, B equals 1 right here, and so on. So you've got the logic expression for S as A complement and B, or A and B complement. And similarly, if you did this for C out, actually it becomes very, very easy, because for C out, you only have one location where C out is 1, right? Only one spot. And for C out to be 1, A and B both have to be 1. So the logic expression for C out is A and B. That's it. What is complement? Well, that's an inverter. A NOT gate or inverter will give us the complement operation. So if that's the symbol, triangle followed by a bubble, the bubble in front of the triangle indicates inversion. So if X, a binary input variable, goes in, X complement comes out. So if 0 goes in, 1 comes out, 1 goes in, 0 comes out. 0 complement is 1, 1 complement is 0. AND gate is represented by this big D. Two inputs here, X and Y. Those are two binary input variables. Z is your binary output variable. Then the relationship between Z, X, and Y is Z equals X and Y, represented using this dot sign. The triangle, if it doesn't have any bubble, that indicates a buffer. More about a buffer later on. So it doesn't change the logic. It actually benefits in solidifying a logic level. More about the buffer later on. So that's your AND gate, symbol expression. OR gate, the symbol is slightly different. Over here you have got a triangle and an arc on the input side. Over here my inputs are X1 and Y1, output is Z1. How can I write it in terms of logic expression? I can say Z1, my output is X1 plus Y1. So this is not an arithmetic plus. This is a logical Boolean plus. So this is a logical operation, logical OR. These are your three basic gates: NOT gate, AND gate, and OR gate. You can design every logic expression using these three basic gates. There are other ways of doing this as well, but using these three basic gates, you can do it. Symbols and their notation. Now, we had two expressions, sum equals A complement and B, or A and B complement. And we also had, for carry out, another expression, A and B. Now, if that is the symbol for NOT gate, where X goes in and X complement comes out, sometimes X complement is represented as X prime. Right? That's okay. We are going to be using this. Sometimes the book also uses this at times. So just be aware that either one of them can be used. Now, what do we need? I want to attempt to draw a logic diagram of my half adder. Right? So at the beginning, I started off with a box, and here is my box. That's my half adder. All of this is inside that half adder. How did I draw that? Well, the first thing that I did was this. I took my two inputs A and B and I drew two vertical lines for A and B. And parallel to those vertical lines, I also put two NOT gates, triangle followed by a bubble. And I drew them vertically down as well. So I've got A complement ready. B and B complement ready. Then I drew three AND gates. Why did I do three AND gates? I needed one for this, and one for this, right? So I got one for this, and one for that. So I took A complement and B. So what do I have at the first AND gate? What is the output of the first AND gate? I got A complement there and I got B there. For the second AND gate, what did I have? I have A and then I have B complement. For the last AND gate, what do I have? A and B. A and B is sum. So I've got sum. S is actually A complement and B, or A and B complement based on the expression. So that's my sum. So that's how you would go from a truth table to a logic expression to a logic diagram using the basic gate symbols. All right, so I hope you found this discussion helpful. Let me stop recording here.